So when we write an equation for the dissociation of a weak acid or a weak base, then we don't use an arrow. We use an arrow pointing from the reagents to the products. We use or a double-ended arrow, or very commonly, this double arrow. What does that mean? It means that in solution you have hydrogen ions, H3O+, you have anions, whichever conjugate base of the acid you have dissolved, but you still have a certain amount of the acid you started with. Some of that acid has not split into ions, has not dissociated, has not ionized, is still dissolving water, but as a compound, just surrounded by the molecules of water. So how do you know how much has dissociated, how much has not dissociated? Well, each acid is different, and some acids are weaker than others. We define something called acidity constant, and the acidity constant just tells you the proportion of products, the ions, to reagent, the amount of acid that is left in solution. And it depends on the temperature. It changes with temperature, because acids will, and the same with bases, will ionize more or less depending on the temperature of the water. And that's something that you can measure. So you can do this reaction at a particular temperature. You can measure the amount of hydrogen ions and conjugate base you've got, and that gives you a value for the acidity constant at that temperature, and this tabulated data that you can find in books and handbooks, etc. And that's what it tells you. The hydrogen ions, the conjugate times, this should be there should be a times here in case you didn't notice. So the concentration of the hydrogen ions times the concentration of the conjugate base you have formed, divided by the concentration of the acid when the reaction has taken place. So if I ask you, do you think that, what does the acidity constant tells you? If you have a large acidity constant and a smaller acidity constant, so you have two acids, one has a large acidity constant, another one has a small one, which one would be the strongest? They would all be weak acids because they wouldn't have acidity constant if they weren't weak, but which one would be stronger? If you have the one with the larger acidity constant or the one with the smaller one? Well, hopefully you have a little think about what it means. If you have a large acidity constant, what does it mean? That the numerator, the part at the top, is larger, and that means that you have more ionized acid, so it means that it's stronger. If you have a small acidity constant, what happens? Well, that the acid, that the denominator, the bottom part of this equation, is larger. That gives you a smaller acidity constant. That means that the acid has not dissociated so much. So yes, if you have an acidity constant for an acid, that means that acid is weak. If not, they wouldn't have it. But within being a weak acid, there is a level of strength. Some are stronger than others, within being all weak. So the larger the acidity constant, the stronger that weak acid is going to be. And we normally, as you will notice, well, we'll show you a few acidity constants later on. The numbers are a little bit cumbersome. For example, the acidity constant for acetic acid is 1.8, 10 to the minus 5. There are 10 to the minus 7, 10 to the minus 11, 10 to the minus 12. They are not easy numbers to work with. So typically you see in many places that we don't work with the acidity constant. We work with minus log on base 10 on the acidity constant. So minus log, what we call natural log, so the negative natural log of the acidity constant, and we call this pKa. And you will see in many tables that they don't give you the value of the acidity constant, they give you minus log of the acidity constant, and they call it pKa. You can have similar, what I've said about acids, you can say about bases. They have basicity constants, and typically you don't work with you won't get the data from the constant. You will get minus log on base 10 of the constant. And why do we work with minus log on base 10? Because if you do the minus log on base 10 of if you do the minus log of 1.8 into the minus 5, that's 4.76. So it's a much nicer number to work with and to compare two acidity constants, you know, minus 5 and minus 6 or 2 point something. Is much easier to compare to 4, 5, 6, 7. It also has an advantage that we will look at later on, that that minus log of the acidity constant, that pKa, can be related to the pH of the solution. And more about that in a later slide, so keep that in mind. We don't work with acidity constants. We very commonly work with minus log on base 10 of the acidity constants, and we call that pKa. And you can define for bases pKb, minus log of the basicity constant. So just to have a little bit of practice, I'm going to ask you to stop the video now and have a go at this exercise. Can I ask you to write an expression for the first acidity constant of carbonic acid, H2CO3, and the second acidity constant? Stop the video now, please. Okay, so if I tackle Ka1 first, so the first acidity constant, it will be the concentration of the two ionic species I've generated. So the concentration, remember, or maybe you don't know, and I'm just telling you for the first time here, that the square brackets around a compound means, or an ion, means concentration. So the concentration of the hydrogen ions you have then generated, and the concentrations of the, in this case, it's called hydrogen carbonate anion. Divided by, if you remember, we don't look at the water, we only look at the well, in this case, the acid, carbonic acid, the concentration of H2CO3. And that would be the first acidity constant. In a similar fashion, if I wanted to write the second acidity constant for acetic acid, carbonic acid, sorry, I would write the products, the concentration, the product of the concentration of the products. In this case are, again, the hydrogen ion, and in this case this is the ion carbonate, and again the square brackets means concentrations, divided by the concentration of the acid, and the acid is my bicarbonate, hydrogen carbonate, if you prefer to use the proper UPAC name, anion. So that would be the expressions for the acidity constants for the first and second ionization of carbonic acid. Because you can have mono, di, tri, polyprotic acid, if you have a monoprotic acid, it only has one hydrogen ion, you will only have one acidity constant. If you have di or a triprotic acid or polyprotic acid, you will have as many acidity constants as hydrogens that acid can donate. And yes, acids can have more than one value for the acidity constant. And as I mentioned before, or we mentioned before in a previous slide, the acidity constant is related to the strength of the acid. The greater the constant, the more product you've got. So that means the greater the strength of the acid. Within the, keeping in mind that they are all weak because they have an acidity constant, but within being weak, there are slightly stronger ones than the other. So if you compare 10 to the minus 7 and 10 to the minus 11, 10 to the minus 7 is 5 order of magnitudes larger than 10 to minus 11. So carbonic acid, the first acidity constant, that reaction is much stronger than the second reaction, which is the reaction of the hydrogen carbonate to liberate that another hydrogen ion. So you can compare the acidity constants, and the one that has the largest constant is the stronger of those acids. And as you can, and this is common, this pattern that the first acidity constant is larger than the second one, and you will see later on the second one larger than the third one, etc., is quite common. It becomes more and more difficult for these for the acid species to donate a hydrogen to the water, or for the water to take away a hydrogen ion from the acid, because you start generating negative species with a negative charge. So you have a species that has a negative charge, and the water is trying to take another hydrogen ion from that species to generate a species that is still more negatively charged. So it becomes more and more difficult to take those hydrogens. So this pattern of the first acidity constant being larger than the second one, and the second larger than the third one, etc., etc., is very common.